some of the data science processes that use it. Things which are coming up is fundamentals of just signing up for fun and check out here. So upcoming talk.
Thanks for coming. Happy to be here. Especially thanks for coming on a really nice Friday afternoon. So I appreciate everyone showing up. Some quick sort of background about myself. So I lead a data science team and then some other groups that aren't sort of related to data science within the patents organization at Google. I've been there for coming up on 4 years, and before that I've done sort of data science in a few different capacities. I did some insurance work, I've done some intelligence work, some social media analytics, so sort of a bunch of industries. My main technical background is actually political science. I did a lot of forecasting models. That was my sort of main introduction into this type of thing. And yeah, so happy to sort of address questions, comments related to other industries outside of tech or patents, and so I'll do the best I can if folks have those types of questions. But I'm not going to talk much at all about my day-to-day work or Google in general. Instead, I'm going to talk about lessons learned from my experience, but really focusing on what I think of as like a distinct type of data science that's actually probably the most common type of data science that exists in industry. And so what I call this is expert decision making, and explicitly, so my talk specifically is how to do data science and how to think of data science and analytics when you find yourself in this context where you're trying to actually aid expert decision making. And we'll spend some time getting into more detail of what this means because it's not obvious by the title. Okay, so to do that and to provide some more context, let's take a minute and just think to ourselves when we think about data science and we think about data science success stories, what are some things that come to mind? Okay, sure, we can do a Q&A. Or volunteer, yep.
Moneyball.
Okay, but what specifically about Moneyball?
Basically just finding a different metric that was previously undervalued and then realizing that it was undervalued and focusing on that. So
Okay. Yep, so that's a good example. So just to repeat, finding examples of some metrics that maybe weren't used as measures of success and then starting to measure those and maybe then replacing some of the more antiquated measures. Yep, and we'll talk about stuff like that in a bit. Any other examples of like classic data science success stories from this industry? Yep. Like the election forecasting? Okay. Anyone else? Okay, so these actually, I'm glad you guys brought both of those 2 points up. Those generally aren't the first things when I do this talk that audiences highlight. Normally what audiences highlight or what people think about and what I think about are things like recommendation systems, right? So when you go log on to Amazon or Netflix or basically almost any e-commerce or content site online, you do a bunch of stuff, you create a profile, you watch some movies, maybe you like some things, and then very quickly thereafter you get suggested content, right? Users like you also liked like this, and this is one of the big sort of one of the first instances of sort of algorithms adding direct business value, and it really helped Netflix become what they are today. I think of things like ads ranking. So when you are on a search engine or Google or anything, and you search for something, ads pop up on the site, or if you navigate to any website, ads pop up on the site. And so then the question is, well, how do those ads get placed? And it's complicated, but they're There are algorithms that are looking at your search query, looking at your past search histories, looking at your cookies, that type of thing, to try to make predictions on what type of ads you're most likely to click on. So ads is another example. Self-driving cars people bring up a lot, which is sort of the algorithmic guts of how you interpret the world around you, and then actually communicate back to the car to make decisions. And so generally speaking, I think when most folks think of data science success stories, they think of things that I would classify as fully automated systems, where the algorithm is making a prediction, and that prediction is automatically surfaced to the user. So if you're on Netflix and there's the suggested content, there's no human overriding that, right? It's the model built a prediction, the prediction is surfaced directly to the user. Same with ads, there's no human who's overriding that. There's no human who you have to convince whether or not that ad should be surfaced. It just is surfaced. Self-driving cars, the same way. There's no human. Ultimately, there's not going to be a human to override it. It's just the car is going to drive itself. Yep.
So when I use Amazon, it'll sometimes say, was this content relevant?
Mm-hmm.
So I'm a human, and in that case, am I at least partially overriding it?
Exactly. That's a good question. So you're the user, and when you say yes, it was, no, it wasn't, that's then being pumped back into the system. Then there's no human on the other side of the equation, right? So it's the side making the recommendation or the suggestions. And so what we can then think of is basically every system that's an algorithm or a data science sort of application follows these 4 steps. And I would take it a step further to say that not only does every algorithmic system follow these 4 steps, but this is generally how humans make decisions as well. Right? When you all had to decide whether you were going to come to this session or where to sit, you generally followed the same approach, which is you collected some information, you maybe read the brochure, you store that in your mind, you inferred and you analyzed it, and you maybe then thought to yourself, well, does this talk seem like it's going to be interesting? Because my other options are, I could go to class, or I could go outside, or I could go for a run. And then you made a decision, and then you acted on it, and you decided to come here. So these 4 steps, I think, are generally ubiquitous in all decision making, but they're especially important for this talk and to draw the distinction between fully automated versus expert support, which is in these fully automated systems. So the example of ads placement, the example of self-driving cars, the example of recommendation systems, all the steps along the way are more or less fully automated, which is information's collected in sort of an automated fashion. There's no human conducting an interview and manually entering information. Like, yes, the user has to fill out a profile. Yes, the user has to click, but that information is stored or is collected. That information is stored on physical devices or in the cloud or in some database somewhere. And the inference is what we think of generally as like the algorithmic layer, how that data is analyzed, how trends and patterns are identified, and how predictions are made is all automated. And then most importantly for this talk, the action, which is to say the thing that you're deciding what to do. In the example of recommendation system, it's actually showing that piece of content on the screen. In the case of a self-driving car, it's actually the car turning. There's no human in between the algorithm and the actual sort of manifestation of the prediction that's being made. It's all fully automated. So does that generally make sense to folks? Okay. This is very different than what I call expert support systems, which are a human, which is the first 3 steps happen generally in an automated manner, but ultimately the output of the prediction, the output of the algorithm is then sent to a human, and it's up to that human to decide whether or not they want to act on the information or how they're going to act on that information. This is probably the most businesses live squarely in this world where you do a bunch of stuff. You collect data, you store data, you build a model, you build a dashboard, you build a report, but ultimately you then share that with a decision maker, and it's up to them to figure out how they want to use that data and how they want to alter their decision based on that information. Okay, so some examples. So this is now connecting to my background or my current job, which is in a legal department. This is how software for lawyers generally works, is that there's lots of new legal tech. So legal tech is kind of a growing industry, and all of these systems share data, share analytics, share predictions, but almost none of them are fully automated. It's generally does all that stuff to give the information to a lawyer so that a lawyer can generally make a better decision. All right, but there's still a human who has to interpret the output of the data. Coaches, so this is the Moneyball example, and we'll get into this in a bit more detail, but no teams are actually relying solely on the algorithm to make decisions. So if they were, then you'd imagine a scenario where like a switch was called in a baseball game and the coach had no power to override. That doesn't happen, right? There's data and analytics that are shared with coaches and general managers, but it's still up to them to make the final decision of how they're going to use it. Doctors, similar idea. There's lots and lots of technology and investment being made, especially so radiology is one of the most sort of intense research areas in medicine right now. But the idea, at least right now, is that it's still suggestions, but the doctor gets to use their discretion on how to interpret the results. There's very few medical scenarios where an algorithm's actually making a decision that can't be overridden by a human. Okay, so this is so just again to hammer home the difference. In fully automated, there is no human. It's the algorithm makes a prediction, and that prediction is acted on. Versus expert support, which is the terminal node on your technological deliverable is sent to a human, and it's up to that human to decide how to interpret that information and how to act on it accordingly. So that distinction generally make sense? Okay. Okay, so here's an example, another sports example. Has anyone heard of this, the fourth down bot? I think, okay, one person, two, a few more. Okay, that's fewer than some rooms, but more than some rooms. Okay, so let's give a quick overview of what this is. I actually think they deprecated this, but what it was most people are familiar with American football, like most of the room. So every play, right, you generally have a few options. You can run a traditional play, you can kick a field goal, or you can punt, which is basically the three options. And generally, fourth down is the down where the coaches have to make a decision to do one of those three things. You run a traditional play, you kick a field goal, or you punt. And coaches are famous for making decisions that maybe aren't in line with what the data would suggest the optimal decision would be. And so a team of folks essentially built this tool where they collected in-game information from like tens of thousands of games or hundreds of thousands of plays from maybe thousands of games. And they built a model that basically said what decision would maximize the likelihood of winning the game, and it was basically punt, kick, or field goal, or go for it. The general takeaway is that coaches tend to be way too conservative. They tend to punt way more frequently than they should, and there's various reasons that we could get into in terms of why that's the case. But this was an example of the differences between expert support systems and fully automated systems, where if this was a fully automated system and maybe instead of a physical football game, it was like an e-sport or something, you might imagine a scenario where no coach would override this decision, where if the data suggested you punt, you punt. If the data suggested you go for it, and there's no manual override. But that's not the case in professional sports, right? So coaches had access to this model live in the games, but they still had to decide whether or not they wanted to trust the data or override it with their own decision. And so this just highlights, in a real-world example, the difference between these fully automated versus expert support environments. Okay, so now we're going to jump into 4 best practices. If you find yourself in this world, which I suspect, how many of you are students here? Okay, so I suspect at least half of the students are going to find themselves in a world where their first job or your first job out, you're going to be in a company where you're building these types of tools. You're building sort of models, you're building dashboards, you're running reports, you're doing analytics, but ultimately you're servicing those to some executive or some sort of senior decision maker, and it's up to them to decide how to use it. That's probably going to be about half of you, and the other half might work in a more like directly applied scenario. But if you find yourself in this role, we're going to get into kind of 4 best practices on how to be as impactful as possible. Okay, first role is when you're in these expert support scenarios, establish the rules of the game and keep score, which is figure out what is the decision that the expert actually has to make, and how are you going to evaluate how well they actually made that decision. So this is something I think might be surprising. is a lot of times, a lot of decisions that are made in business, people haven't even agreed ex ante how they're going to determine if that decision was the right decision or the wrong decision. Then if you find yourself in that place, it's very, very hard for you to demonstrate the value of your own work, right? So you imagine a scenario or imagine two versions of the world, right? One version of the world where the decision maker doesn't have the model you built, doesn't have the analytics report that you provided, and a second model of the world where they did have that. You want to create a scenario, you want to create a situation where you can unequivocally demonstrate the value that your model provided, and the only way that you can do that is if you set out up front how you're going to measure the success of that decision. And so the idea with this slide is, are folks familiar with the HIPPO, or have anyone heard that? I always mess this up, but it's highest paid person's opinion, so HIPPO. You want to avoid a scenario where the quality of the decision is evaluated based on whatever the highest paid person's opinion is. That's how most of business still works. It's very, very, very hard for you ever to demonstrate the value you provided if that's the case, right? So the idea is always try to establish some objective evaluation criteria before you generate any report or you build any model or you do any sort of data science deliverable with your company. It's hard. You're often going to face a lot of pushback. But the idea here is that if you have something like root mean squared error as a way to evaluate performance, then there's less likelihood that there's going to be disagreement down the road on how well your model or your tool performed. If you're relying on a HIPPO, it's a much more risky proposition for your work product. Okay, check marks. Okay, this is another thing. So are folks familiar with what this image on the left is? It's a little outdated. When I first put this presentation together, it was, yeah, this was cutting edge when I first put this together. So this is Deep Dream, which was a tool that Google released, which was a deep learning implementation where you can combine multiple images, and it kind of creates a hybrid. And so this was Starry Night mixed with Bosch or some kind of other. If you look closely, it's Starry Night, but there's like little beasts and stuff superimposed. And this was really cool, and it's really fun, and it was like really complicated deep learning technology. But the idea of favor simplicity is start with always favor the most straightforward way to satisfy a task and only add complication when you absolutely need to. So don't jump straight to some like convolutional neural net, 8,000 layer thing if you can write a 5-line SQL query that does the job better. I think especially as you're starting out, your first couple years of an applied data science position, there's always the urge to do complicated things, to demonstrate all of the sophistication that you have, all the tools you know how to run, all of the algorithms you know how to build. And that's fine, but when you're actually doing it for real, always favor the most basic, simple approach and only add complexity when you need to, especially when you're in this expert support role, because the value of explainability is so high. People often, even if your model's generating good results, oftentimes if you can't explain how you got there, people won't trust it and they might just dismiss it out of hand. So if you're building models for a human to improve their decision making, it's extra important to favor simplicity and fight the urge to add in complexity unless you absolutely need to. Okay, so I'm probably, okay, does anyone know who this is? Okay, he's a fairly obscure figure for various reasons. Hope I get this story right now that we're being recorded. So apologies if I get any aspects of this wrong. But this guy's name is Dr. Semmelweis. He was a doctor, I think Romania, but might have been Hungary, in the 19th century. And I don't know, for folks who maybe study the history of medicine or have heard about or sort of read about this stuff, or maybe have read about the Civil War or presidential assassinations, or folks will be familiar with the idea that the belief in germs is a fairly novel concept in the medical community. So even throughout the Civil War, throughout the 19th century, people didn't it was not mainstream belief that the existence of germs was not a mainstream medical belief. There were all sorts of other theories that folks tried to use to explain the spread of infection and infectious diseases, but germs, it was not a mainstream thing. And so this guy was a doctor in a town that had two main maternity wards, so where women would go and deliver their babies. And he he recognized meaningful variance in the infant mortality and mother mortality rate between these two clinics. And he thought about it a lot, investigated a lot, and one of the clinics was staffed primarily by midwives, right? And one was staffed by medical students. And the hospital that was staffed by medical students had a considerably higher infant mortality rate than the hospital staffed by the midwives. And so he spent a lot of time trying to figure out why this was the case. And then he found out that the medical students were often coming directly from their cadaver class before they went to deliver babies, and they weren't washing their hands. So again, this was before people knew what germs were, so it wasn't clear that that was the link, but he identified that this was the case. And then he did a bunch of experiments with like sort of primitive sanitation type things, and found that washing hands dramatically reduced the infant mortality rate for the folks coming from the morgue for the medical students. And so he had, at the time, one of the greatest, looking at it now, one of the greatest discoveries in the history of medicine. And now it would seem obvious that if he discovered that finding, everybody would embrace it, and everyone would believe him, and hospitals would change their protocols. And this was not the case. And so what he did with this discovery is he went through the established sort of medical journals. He went to the established medical conferences. He assumed that if he spread the word, people would adopt his suggestion, which is essentially wash your hands before you deliver babies. Instead, he was sort of flatly rejected by the medical community. He was deemed a fraud. He was deemed whatever bad word you could think of. He was sort of ostracized from the medical community. They didn't believe him. And one of the reasons that they didn't believe him is because the people who were sort of the incumbents and the senior people amongst the established medical community had different theories on how disease spread. And so for them to acknowledge that he was right they would have had to also acknowledge that they were wrong. And the hardest thing to do is get people to believe in something that's against their economic best interests. And so he was rejected out of hand. So this is a sad story, he then went insane because no one would listen to him. And there's lots of sort of anecdotes that are really sad of like, mothers who had to deliver a baby would get sent to one of the two places, and the ones who got sent to the clinic where the medical students were delivering the babies, they would like get on their knees and beg and plead not to have to go there because they all knew as well that the chances of something bad happening were higher there. So it was a nasty situation. So he went insane, and like literally shortly after he made these discoveries, got put into an insane asylum because he just couldn't understand why people wouldn't listen to him, why no one would do what he suggested, and then he died like very quickly thereafter in an insane asylum. And it's okay. So that's a sad story. So but here's why I tell it. Well, it's interesting, but the main reason I tell it and why the slide is called "Be Creative to Drive Outcomes" is because you would think that a finding like that should just speak for itself. That your work as a data scientist would be over. You found the greatest finding in the history of the world. That's it. You turn in your report. You share your code, you publish some web app, and like you're done. Congrats, pay me, give me my bonus. I've done the greatest job ever. And if you were in a fully automated system, that would be the case, right? So if okay, here, one sec here. Okay, so now imagine like instead of studying medicine, he was building a new sort of image classification algorithm, or a new self-driving car algorithm, or a new ads ranking algorithm. There would be almost zero chance that his findings wouldn't be embraced and his model wouldn't be pushed into production and he wouldn't get some massive 9-figure stock option or something. But this is different, right? This is a scenario where it's not just how good of findings do you have, it's did you get people to actually act on your findings? And so if folks here are find themselves working in a role, right, in this type of role where it is an expert support system, if you aren't able to get people to believe your findings, act on your findings, alter their behavior based on your findings or your model or your analysis, you've added zero value to the company, right? So it's not enough just to do really good technical work if you can't get people to use it. And so if we then take a step back and say, well, if he had a bit of a different mindset, and if his goal was purely to get people, so he had this finding that if you just wash your hands, the mortality rate goes down. What could he have done differently if his sole goal was to get people to wash their hands? Well,
He could just like not give them a conclusion, but present it as an experiment.
Sure.
Run.
Yeah, and so something like that is what the first thing that came to mind for me. So here's one example of what he could have done. He could have challenged the hospital owners to a bet, and he could have said, let's have a bet that that infant mortality rate will be lower in the bad hospital within a month than it is in the good hospital, and if we win the bet, I'll put up the money. If we win the bet, I get my money back and you get the profits. If we lose the bet, it's on me. I'll pay for it. And all you have to do, if you accept that, all you have to do is promise me, I'll put the money up front, but you have to wash, your people in your lab have to wash their hands. There's nothing to lose. You only have something to gain. Let's just see how this goes for a month. So something like that, which is, it's kind of silly, but it's just a different way of thinking about how to actually get people to believe and get people to alter their behavior based on what you have found. It's highlighting that it's generally not, it's often not enough just to show some of the findings and assume they're gonna use them. You often have to get more creative and think outside the box. And so I suspect folks, a year or two down the road, when you're sort of in an applied position, will have a similar deal where you'll have a really good model, you have really good findings, and you just can't get anybody to listen to you. And if there's one takeaway from this talk, it's going to be what to do in that situation. If you find yourself in a situation where you think you have a really good finding, and maybe it's about where you should be investing marketing dollars or what ad campaign you should run, and you feel very strongly that you're right, and the data supports that you're right, but the decision makers just don't believe you. Again, if there's one takeaway, it's take a step back and change course. Try a different approach. Try something more creative than just showing them the results and repeating the same arguments. I've been there. It's really hard. But if your results are correct, if your beliefs are correct, you've got to just find a more creative way to get someone to listen to you and actually heed your advice. Oh, okay. Yeah, so this is the find good findings like that, but maybe don't take his route in terms of how he actually disseminated that information. Okay, last point is, this is an example of, and this was an article, so there's no like secret insider information here. This is just citing an article from 2014 or 2016, a couple years ago, that Google, it was basically when they were designing self-driving cars, there had historically been steering wheels and there was a human in the car, and this is in closed loops and like not on public streets, so this is controlled environments and so on and so forth. But what they found with the steering wheel and humans that could override the self-driving aspects, they found that the humans, when they intervened, actually created more accidents than they avoided. Right, so there was this pre-held belief that having a human in the loop would actually increase the value of the system, and what they found was that it didn't actually increase the value of the system, and so they removed the steering wheel. This is a common thing in lots of industries that maybe are averse to or have not historically been technology industries, is that there often is this very strong belief that you need a human in the loop because the human adds value, the human can understand concepts that an algorithm can't, the human has a better sense for these things. You heard very similar arguments with Go, right, the game of Go. So have folks heard of AlphaGo? Okay. So the general idea was that there were some people who thought the game of Go required some humanistic understanding of something that a computer could never replicate. And so there was this belief that we were still a decade away from being able to beat Go with an algorithm. And so this is kind of a similar idea where there's lots of industries and lots of examples where lots of people have this deeply held pre-existing belief that there's some human element that an algorithm can't pick up, and you need a human to be the final decision maker. This is very common or very relevant right now in medicine. So like radiology, you're starting to see some of this where there's lots of studies now demonstrating that some deep learning systems can do better radiology diagnoses than the human experts, but you're still getting pushed back. And a lot of it's valid, but some of it maybe is less valid if you were going to be objective about it. But the main takeaway here is that humans don't always actually add value in these systems. And you should always be asking yourself, like, is the human adding value? Is the human not adding value? And be mentally prepared to essentially remove the steering wheel or remove the human from the loop. And again, like, you don't want to do this. There are ways to do this right and ways to do this wrong. And there are some industries where it's way more sensitive and some industries where it's way less sensitive. But it's just, the idea here is to always be thinking of whether or not the human decision maker is actually adding value, or maybe they're not adding value, and to think about experiments that you could potentially run to test this. And so some of these experiments might be fairly straightforward. You set up a test case where the predictions from your algorithm it's just what you do, and in another scenario where those predictions are fed to a human, and the human gets to tweak them as they see fit, and then you just see which led to better outcomes over time. So there's ways to set this up, but the idea is the takeaway from this slide is just to mentally keep in mind that just because the status quo is such that the output of your algorithm is sent to a human to make the final call, that's not always actually adding value. There might be times when that's actually decreasing value, and in those instances, we should try to set up experiments and be open to the possibility that maybe it's time to remove the steering wheel. Okay, that was quick. Sorry, that was about half an hour, so plenty of time for questions if there are any. Yep.
I'm wondering, for the robot for the baseball thing, would they incorporate whether this prediction has been accepted by the human coaches into their loss function?
Yeah, that's a good idea. So the question was, did the fourth down bot algorithm actually then measure whether the coaches did the decision it wanted and then incorporate that decision back into their loss function or use that to update the predictions? I don't know. That's a good question. I don't think so, but that would be really interesting to then see the win rate. I would guess sample size might not be high enough, but you could imagine if they did do that, then you could compare the sort of win rate of the folks who followed it versus the people who didn't. I think that'd be interesting. I don't know if they did it though. Yeah.
Do you have any other examples of overcoming a resistance to act on findings?
Yeah, it can be really hard, or it's almost always really hard. I think the biggest, it becomes the hardest when acting on the data or the sort of data-driven suggestion, when acting on that decreases the value of the expert, it can be very hard, because then you're in the scenario where it's literally against the economic best interest of the expert to defer to the algorithm, because then you either don't need them or you don't need them as much, and then the next step then is, well, do we need to employ them or do we need to pay them as much? So I think the thing to try to do, and it can be very hard, is to align incentives accordingly, which is maybe try to find ways to make it so that if if an expert uses the algorithm and they do better, it's going to be very hard to make it in their economic best interest to do so, and that often means you spend more time up front figuring out the evaluation criteria. And so if there's an objective evaluation criteria, then a human might be more incentivized to believe the algorithm, because they're getting evaluated based on the quality of their findings, not on something else. It's a hard question, and I'm giving a terrible rambling answer. It's very hard. Yeah, the best advice I can give is try to align incentives before you build the model. Try to spend time. Yeah, okay. So here's a couple more direct suggestions. Build relationships with those people. Make sure they trust you. Make sure you trust them. Build that dynamic so you're part. So you feel like you're part of the same team. You want to avoid scenarios where, yeah, you want to avoid scenarios almost at all costs where the status quo expert decision makers feel like it's you versus them, where it's the machines are, there's a team of people who's trying to build algorithms, they're trying to come for my job. You're going to face resistance nonstop in that instance. So trying to get out in front of that, which is get on the same team, build those relationships, and create an environment amongst, or try to work with them to create an environment amongst sort of senior leadership or the most senior tier where if they use the algorithm, if they defer to the algorithm and they make better decisions, that they get rewarded for that and not punished for that. I think that's the biggest, that's the biggest thing. And you want to do as much of that before you start building your model, before you start collecting data, before you start running analytics as possible. If you wait till the end, it's harder. So I guess the main takeaways there, yeah, is figure out who those decision makers who are going to use your tool are up front, and talk to them before you start building anything, and try to get on the same team and make sure that your incentives are aligned to avoid at all costs this feeling of like them versus some new hotshot data scientist who's trying to replace my job, because those scenarios are almost always not going to go well. Yep.
Your second point was favor simplicity.
Mm-hmm.
It sounded more like favor clarity or favor explainability.
Yeah, no, I think I want to keep it at favor simplicity. Not so. I guess I highlighted that one of the benefits of simplicity is explainability. Oftentimes, explainability is very valuable. Not always. It's not always needed. If your predictive accuracy is sufficiently high, people generally don't care if it was a black box. In some instances, they don't care if it was a black box. But the other benefit of simplicity, yeah. So one benefit of simplicity is explainability. The other benefit, which is often bigger, is ease of maintainability. So the general rule of thumb is any additional technical complexity, it takes you more time to implement initially, and it's going to be twice as hard to maintain because it's more complicated. The other benefit is it increases the likelihood that other people and your other teammates will be able to get up and running on it quickly. So you eliminate what's commonly referred to as the bus count issue. Have people heard of the bus count issue? Okay, so this is so there's, at Google we use the lottery, they call it the lottery problem, which is the more positive spin. The bus count issue is essentially, what if the person who runs the thing gets hit by a bus, and you don't want a bus count of 1 because then if they get hit by a bus, there's no one else who can run that tool. At Google we call it the lottery problem, which is what if that person won the lottery and quit the next day? Which is obviously a more pleasant spin, but that also is something to account for. When people build really complex systems or over-engineer them, it's much harder to build in redundancies to make sure other people know how to run them. So those are the 3 main reasons to favor simplicity. 1, explainability. 2, sort of implementability and maintainability. And then 3, sort of explainability to your peers so that someone else knows how to run these things. Yep.
This is going to sound like an interview question.
Yeah, that's fine. Yes.
So I'm just curious about the persuasion and communication side of this. So the scenario is, if you had 100 skill points, you said, to like make an optimal data scientist at Google or somewhere, what % of those points would you assign to modeling ability?
Yep.
And versus like communication persuasion?
Yeah, that's a really good question. And I think it's very dependent on what the role is. And I would add one more flavor to that, or actually no, I might bring in one more flavor, but I think it's really, really dependent on what the requirements are. So there's some people who are data scientists or who do data science whose jobs are like very conducive to them kind of heads down, headphones on, 40 hours a week. So this might be if you're part of an applied research team or more. So big companies will often have teams that do basically base research, which is kind of like academics but in-house. Verbal communication, not as important. then lots of work will be more kind of on the engineering heavy side. So someone built a model and now it's your job to kind of implement it or push it to production. Communication might not be as critical, or communicating with the business might not be as critical. Then there's roles where it's like you're the one data scientist at a marketing company, and they're a traditional marketing company, but they know that they need to start using data and analytics more aggressively, so you're the first person they hire. There, I would say like 80 of those points should be communication, because what they probably need is someone who understands relational databases, can run a SQL query, maybe run a logistic regression, but really communicate those results. So I think it's really role dependent. And that's a question where if you're, as your so for the folks who are going to be entering the job market soon, a manager should be able to answer that question very crisply, which is like, what's the distribution of skills that are optimal for this role, and how much do you value sort of communication with the business versus like heads down technical? If people waver on that, it's a bit of a red flag. People should know. The other thing I'll bring up is you didn't ask this specifically, but this goes to the question of how you'd want to allocate sort of skill points for a given job. Is I would pay close attention to what is the thing that is being analyzed. So you can imagine some roles. So like let's say you're working for a hedge fund doing high frequency trading. It's really like you're analyzing electrons, or you're analyzing like very low level kind of speed computation things. But let's imagine the other world where you're doing marketing campaigns or something. You're trying to influence people's behavior. And so I would encourage people to when you're applying for jobs or thinking about roles, is to know what interests you. So if you're interested in understanding like how humans interact, how they do, or what motivates people, then a role where you're like a back-end engineer on a image detection app might not be optimal for you. But if you're someone who really just likes the more technical side, or likes physics or geology or units of analysis that aren't humans, then you might want to go in that role, because then you might hate if you constantly are having to analyze human behavior because it's messy in distinct ways. So that was the slightly oversharing answer to your question. But does that make sense? Okay. Yep.
So couldn't you do a mixture of both? Have like maybe 80% of things decided by an algorithm, and then all the edge cases go to the 20% of edge cases would then go to human arbiters?
Yep, and that's what a lot of systems are. Like the easy cases are done by, so it's like I was going to give an example, but that's a common approach, which is easy questions are handled, or easy use cases are handled automated, and then the hard ones get escalated to person. So like chatbots are kind of like that. So if you say hi, or a better example is you call in and you get the automated voice command, which is like, do you want to change a reservation? Do you want to make a payment? Do you want to do this? All other questions press 0. So that type of approach, in many instances, tends to be very, very successful. Which is if it's low-hanging fruit or one of 3 or 4 like archetypical use cases, you let an algorithm do it, and then the edge cases you get funneled to humans. So I think that often works very well, and is often optimal. I'm happy to answer questions about anything else too. So folks, whatever is fair game. I'll do my best. Yep.
I'm a hiring manager for a company's first data scientist.
Mm-hmm.
There's an unlimited amount of things this person can dig into. We're mid to early stage startup. You've got a rough idea of the profile the architect is looking for. Any advice for that first person that's going to be a maker for?
Yeah, yes, I have strong thoughts about this. What I see companies do a lot, so the biggest mistake that I see commonly made with companies that sound like a similar profile is they think it's something they should do, and I'm not saying this is you, so I don't mean for this to sound accusatory, but a profile I hear a lot is, it's a company that knows they should hire, or strongly believes they should hire a data scientist, that they would benefit from some big data machine learning-y thing, and so they then kind of start, and then the approach is, well, let's hire one person and see how it goes, and see if they can kind of figure out where they're going to fit in, and kind of just let it run. That approach I would strongly advise against. I would say 2 things. One is if you're not clear on like an exact if you're not very clear on what the need is and what areas quickly, I would suggest holding off. So I would suggest holding off to hire as long as you can, using consultants as long as you can, and the first hire, I would err on the side of 1 or 2 levels more senior than you think you need. So the first person, if you bring in a junior person, the likelihood that they have enough sort of corporate savvy professional experience to navigate all the complexities of building a new function is very low. They're probably not going to succeed. So I'd say leverage. My suggestion would be leverage consultants and external non-full-time employees as much as you can, and then only hire when you feel like you need to. And then the first hire should be senior. And if you're not willing to spend the money to get a senior person, then your organization is probably not committed enough to that function to make it work anyway. So if that's the case, then I wouldn't do it. But I would avoid it at all costs, bringing on a junior person as your first hire. Okay. Yep.
So you said your technical background was in forecasting with political science.
Yep.
How did you kind of pivot to data science, or was there a little bit of analytics first? Just general?
Yeah, that's a good question. So when I was getting my PhD, data science wasn't really a term yet. So back then you would call people statisticians or like analysts or actuaries or kind of other things. But in grad school, I took a lot of statistics courses and a bunch of sort of machine learning courses, although back then, or it wasn't that long ago, but they didn't even necessarily call them machine learning. They call them data mining or some other things. I just took a lot of those courses and then a lot of sort of technical methods courses, and then applied them to political data. But it was actually fairly straightforward to transition into industry. But keep in mind, the bar was much lower back then. Like there were no programs like this. Like you were not competing against a lot of people. You were generally at that time, which was, so I've been out for 6 years. You were generally competing against a small pool of people who finished a PhD or a master's program and didn't want to be professors. So there wasn't a lot of competition. There's way more competition now. It's crazy how much more competition there. So it's way harder now, but there's also way more guidance and coursework or programs like this, and like sort of professional mentoring that you can get. So that wasn't that good of an answer. Is that okay? Okay. Yep.
So, gentleman over there mentioned Nate Silver and fighting. So, how could that be so wrong as far as the 2016 election, and how could political forecasting for the Brexit Leave or Remain decision also be so wrong?
Yeah. Okay. I have very strong feelings about Nate Silver, which if we weren't being recorded, I'd be more apt to share. So how are they wrong? They're wrong because it's generally hard to predict these things. I think some ways that polls generally get it wrong is you have to make a lot of assumptions about sampling distributions. You have to make a lot of assumptions that people doing these kind of exit polls and polls are telling you the truth. You have to make you make a lot of assumptions, and they're still probabilistic forecasts. And so there's always uncertainty. It's like playing roulette. Even if you stacked a roulette board with 85% red and 15% black, you're still going to get black. So I think that's often how those forecasts work, where you're making probabilistic forecasts and you expect that you're going to be wrong in proportion to the confidence of your forecast. So part of this it's hard. It's hard to do, and that's the nature of these types of sort of probabilistic forecasts. Is you're always going to get wrong at some point. You hope that you're wrong in proportion to your confidence. And I'll save my strong opinions maybe for offline. Yep.
You mentioned using contractors before you make your first data science hire.
Yep.
So if an organization is just sticking their toe in the water for the first time, how's the smart way to do that? What's the contractor you need? How do you find a good scope of work?
Yeah, I would generally, so I can tell you what I would do. And so I'm biased, so now my response would be, if you find someone who tells you something different, I'll tell you what I would do, and I would suspect most folks would do. If you came to me and said, hey, Jay, we think we have a lot of use cases that would be amenable to a data science person, whether that's a full-time hire or a contractor, what do you think? What I would want to do is come in and spend at least a week embedded with your organization, meet people, talk to people, figure out who those decision makers are, figure out how you're evaluating success, get a sense of the technical people that you have. Do you have an engineering team? I would talk to them, try to figure out who's actually doing what, what's the level of skill, what level of technical debt do you have, what's the level of data that you have. So I think oftentimes some companies just starting either think they have more data than they have, or think they have more data than they have, think they have cleaner data than they have, or think they have data that's more directly related to their use case than they might have, which is all to say the data might not be ready. Then that's then the question becomes, well, how do we get better data, not how do we analyze it? So I would spend the first week or so deeply digging into your organization, meeting people, understanding sort of your technical stack, your existing technical engineers, and then scoping out some first use cases. And making sure that you've established evaluation criteria before I would commit to any project. And part of the reason also I'm saying this is I've done a bunch of consulting, and I've done it wrong. I've done it wrong many times, which is the general way that it goes wrong is someone says, hey, I want you to build a customer segmentation model, and here's our data, and like go. And then you build it, and then you give it to them as like, now what? And then that's it. So this is coming from experience of having done it in ways where I added no value to the organization. No one wants to be in that world, and so I think there's a few little like questions you could probably throw out there which would give the person the opportunity to raise a red flag. One would be you just assign and say, hey, I want you to build a model to do this. If they just say yes, don't use them. That one I can say with very high confidence. There should be 10 to 15 questions that they would ask you before saying yes. And so things like this. So people too eager to just take the work probably need the work, and probably that'd be a bit worrisome. And anyone who isn't asking to meet your existing people and deeply understand how the deliverable is going to fit into your org, I would avoid. Is that useful?
Yeah,
Okay.
that's good.
I guess I can do that. Yeah. Okay. Yeah, communicating uncertainty is very difficult. It's very difficult. I think, one of the things I try to focus on is understanding. Actually, let me pull this. Let's see, I'm trying to pull up a slide. Okay, this is kind of a quick slide here, but I brought this up to say that I think you want to really know, when communicating the uncertainty, I think you really want to know the costs of an error, so the cost of a false positive or a false negative, and what happens in that event. So you can imagine some of the most extreme examples of costly errors would be like medical diagnoses. And when the costs of errors are that high, you communicate uncertainty maybe differently, which is you have different requirements on what level of uncertainty you're willing to accept to actually use that model you built. And so if the cost of errors are extremely high, and in the event of an error, you require crisp explainability, that's something you should know before you try to have that conversation, because then the comfort level of the end person or the end user is going to be much, much lower for uncertainty, which is then maybe you don't even make a push if you can't sort of get more precise confidence bounds. And the other challenge, I think, is the volume of observations. So if you're in a world where you're building a new like ads ranking tool, and you might have billion or hundreds of millions or billions of observations each day, which is to say opportunities to test your algorithm, and the cost of errors is low, like someone didn't click and you lost a penny, it's not the same as getting a medical diagnostic wrong, then you can set up experiments. And so I would try to leverage like actual experiments as much as possible if the risk profile is right. And the higher number of observations you have, generally the higher level of uncertainty you can stomach, because you have lots of chances to basically see where your observations are falling within your sort of confidence bounds. So that's the general advice would be just really make sure you understand the downsides of how costly are errors and how are you in a big data world or a smaller big N world or a small N world in terms of observations? If you're in a small N world, which is someone might only get a few shots a day at making that prediction, then you're going to have a much lower tolerance for uncertainty, and then the communication of it might even be a non-starter. So that's my general advice. So. Okay. Yeah, that's.